Hello, I'm Aubrey Lawson from Clemson University, and today I'm presenting some work I did with my advisor, Dr. Eileen Kraemer, on characterizing student reasoning about concurrency, which was the topic of my dissertation work. Concurrency is pervasive in modern computing systems. Many computations, threads, processes happen at the same time, that is, either at the same time or in an interleaved manner with the goal of increasing throughput and responsiveness. But concurrent programs need to be constructed carefully to ensuring that these multiple computations interact in ways that maintain correctness and promote good performance. Accordingly, concurrency is an important topic in computer science curricula, and understanding how students learn and reason about concurrency is important for instructors to understand in order to teach it well. But concurrency has been a proven difficult topic for both students and instructors. Computational thinking is typically taught as breaking things down into step-by-step tasks, and it's simple until it isn't. Writing a concurrent program might feel a bit more like trying to manage a busy restaurant on a Friday night. Suddenly, you have a stream of food orders that involve different ingredients and preparation, and you have multiple chefs to perform these tasks. The goal is to prepare all the dishes correctly and in a timely fashion, which means the chefs need to be able to move between tasks to avoid conflict. This is what non-deterministic execution looks like in programs. Different correct executions of a program may involve taking different paths through the code, and the output order may vary. From the instructor perspective, they have students with prior programming experience steeped in sequentialist mindsets that they have to transition to a concurrent programming space. Traditional instruction uses analogies such as classical concurrency problems that map concurrency concepts and concerns to real-world scenarios, and they also use informal models like design patterns, which provide general reusable solution templates, or formal models like state models. But concurrency is hard for both instructors and students, and research has proven how difficult the leap to these concepts is. Our initial questions were grounded in a constructivist approach. If we can understand how students reason and the misconceptions they have, we can improve pedagogical content knowledge for instructors. So we developed an overarching research question. What are the salient features of the student process in solving concurrent programming problems? This presentation covers some of the results from my last of 3 studies involving this question. I'd like to quickly pause to address that concurrency is also hard to research. This concept is typically taught in upper-level courses, which tend to be smaller and taken by students at different points in their degree programs. These courses often aren't solely focused on concurrent programming, like the course used in the 2nd and 3rd studies, so opportunities are slim for recruiting students. Further, concurrent programming problems are complex and entail more demands on participants and availability. In the first study, we developed a broad view of student reasoning by replicating a natural language prompt asking undergraduate computing students to describe a solution to a real-world problem involving concurrency. The work was informed by Flowers and Hayes' work that asked, what problem are they solving, and found a significant difference in novices' and experts' interpretations of a problem. We found that students were able to identify the key concurrency-related issue, but struggled to describe a solution, as they often added unnecessary complexity and avoided handling the concurrency-related conflict. In the second study, we wanted to focus on student implementations, where rubber meets the road, so we worked with a concurrent programming course of 24 undergraduate and graduate students, collecting submissions and reflections from 2 classical concurrency programming projects. Similar to Resnick's observations of a sequentialist framework, we found the persistence of Study 1 features, as well as new insights, specifically the implementation of asymmetrical synchronization and conditional logic, and a lack of confidence in modeling materials and student ability to implement them. For my third study, I had the opportunity to collect from the course the students' final exam sessions, which comprised programming a solution to one of 2 classical concurrency problems. In our third study, we sought to study students as they engaged in the full process of understanding a problem description that involves concurrency, and then designing, implementing, and testing their solution. We engaged in a case study of students in one course in the context of a 3.5-hour programming exam. The students chose between Dijkstra's sleeping barber's problem or the single-lane bridge problem. They could work alone or in pairs. We chose the reflexive thematic analysis, as described by Brown and Clark, to generate themes from qualitative data through iterative creation and refinement. Importantly, this supports an inductive approach to generating themes grounded in the data, while also acknowledging the theoretical frameworks that we as researchers bring to our analyses and underpin our observations. Students were asked to think aloud, so we captured their process through audio recording and video capture of their screens. We also collected their final submissions along with the instructor's evaluation notes. We ended up collecting 12 sets of submissions and recordings after the 3 groups that experienced recording errors were excluded. We began familiarizing ourselves with the data by transcribing audio recordings and marking points of interesting discussion. We then worked to identify student tasks through quantitative coding of the audio and screen captures. I developed a revised version of Latoza's developer activity taxonomy to generate a timeline of reading, writing, and testing tasks, and the artifacts involved. Students had access to online class materials as well as prior programming projects, which made identifying their resource usage very interesting. The resulting timelines helped further familiarization with this large data set, and we journaled initial impressions of student tasks. We moved on to systematic coding, which involves the audio recordings, screen capture, transcriptions, timelines, student submissions, and instructor evaluations. I then individually analyzed the materials, iteratively developing codes on student modeling, behavior, and solution features, and journaling initial impressions. This process of coding and journaling was repeated by the second author for code creation. We used codes related to the prior study's features as well as any emergent trends and provided context notes including utterances and intermediate code snippets. To review, the output of each phase was fed back into the analytical process to give as full a picture as possible of student reasoning by contextualizing their behavior and submissions. So then we could generate and refine themes that describe how aspects of student process impacted their struggles and their solutions. We developed themes relating student behavior to impacts on the process and submissions. We found a focus on speed and timing led to poor flow management. The use of overly complex data structures compromised the data integrity. A focus on the realism and the analogies led to convoluted logic. A lack of delocalized plan design led to uncoordinated synchronization and conditional logic. And then students were not motivated to use the provided models, they were rather motivated by their own code. As we started to describe previously found and newfound insights, we developed an emergent code and resulting theme that was incredibly salient, an over-reliance on example output. Students paid a lot of attention to the single example output section of the specification. The section was alongside overall problem descriptions, method breakdowns, skeleton code, and correctness properties. But what I first noticed as a time-consuming task in the revised developer activity taxonomy indicated a student approach with far-reaching consequences. So as we ask, what problem are they solving? Let's look at the problem and solution spaces. The single-lane bridge problem describes a bridge that only allows one flow of traffic at a time. Red cars travel in one direction and blue cars in the other. An appropriate solution controls access to the bridge such that all cars can enter and exit the bridge in a timely fashion without any collisions. The bridge is referred to as the shared data, which is accessed by active entities, here the red and blue cars. Now in the sleeping barbers problem, customers enter a barber shop and wait for service. The shop has multiple barbers who sleep when there are no customers waiting or when they've reached their maximum service time for the day. An appropriate solution facilitates the efficient service of the customers without exceeding the barber's maximum service times. So the shop here has the shared data, including the waiting room and the variables that capture the barbers in their chairs. The active entities are the customers and barbers, as customers contend for seats in the waiting room and barbers contend for customers. When defining a solution, promoting concurrency is key. Suppose each stripe here represents a different interleaving. It's crucial to allow only valid interleavings to avoid safety violations. But this concern taken too far can severely limit concurrency and violate its purpose of improving throughput and responsiveness. A key part of solution implementation is defining the shared data and the active entities that use it. As mentioned, there's typically a symmetry in the form of synchronization, as in this Java-ish example, with await and notify. Lutovsky and Soloway described this organization as delocalized plans, where elements of a unit are in different parts of the code. They found that programmers under stress, such as time pressure, often compromised updates of these elements, leading to mismatched code. So in the case of sleeping barbers, a barber may sleep while waiting on a customer. When a customer arrives, they notify that they are ready. These elements have a natural symmetry, and if a change needs to be made to how service is handled, both elements should be taken into account. And once again, it's important when we're updating the shared data that is being accessed by multiple entities that all correlated variables need to be updated to preserve the state of the program. Thus, certain critical sections of the code need to have synchronized access to avoid invalid interleavings and safety violations. Now, let's take a closer look at an example of this. Imagine your critical section comprises 3 variables. It's important that each active entity, when it's their turn, gets to grab all 3 and no one else updates them. Since they're updated together, everything looks good as the state is updated atomically. Now another solution approach, one taken by some students, was to not synchronize these updates together and instead use atomic variables. In this case, only one active entity could access a variable at a time, but this still leads to uncoordinated updates. For example, an entity might take the first variable and say, "This is mine," and update it. By the time the entity obtains the second variable to update it, another entity has gone and changed the first variable's value. Then, by the time the entity gets to the third variable, another entity has updated the second and third variable. So now, nothing is quite actually what it's meant to be. So what can go wrong here? Well, in the case of the single-lane bridge, there are safety concerns. Red cars and blue cars both think they can go, and there's collisions. There's also liveness concerns. Neither a red nor a blue car think they can go and no one gets to cross the bridge. And there's also fairness concerns. Suppose only ever red cars get to go and then blue cars might get road rage. So with the single-lane bridge problem, it's important that the bridge contains the shared data and manages these critical sections by synchronizing them so that all correlated variables are updated. Then the active entities, the cars, can just call methods to try to access the bridge. Also notice the presence of delocalized plans here. So red enter represents red cars trying to enter, and that contains a wait on the blue exit. Likewise, blue cars waiting to enter are waiting on the red cars to exit. And the sleeping barbers is somewhat similar. Barbers sleep while waiting on customers, and when a customer comes in, they notify to say, "I'm here." So as we looked at the student processes, example output started to make sense of all the features. We found that an over-reliance on it led to a few different things I categorize here. One is a focus on controlling real-world timing and oversimplifications about ordering. Even though the solution needed to focus on synchronization, students focused on actual timing, down to seconds. Some tried to alter sleep calls to affect the processing, and others stated concerns about access control as issues of being too fast. We also noticed that students struggled with analogical reasoning. They struggled to relate their exam problems to other classical programming problems they had encountered in the course and were free to reference. Another finding was a focus on administrative subtasks and coincidental characteristics. Students spent significant time managing the simulation settings and tasks such as output and termination before and often instead of defining logic for the key concurrency-related part of the solution. Students also interpreted the problem in interesting ways that led them to focus on coincidental aspects, such as the bridge's length and the barbershop seat arrangement. Students who over-relied on example output unsurprisingly perceived clean-looking output as the indicator of success, and they sought it out at whatever costs, including edits that compromised the program logic and limiting the simulation settings used in testing. Finally, students used the single example output as the ground truth for programming decisions, often changing the skeleton and altering synchronization and conditional logic based on assumptions from the single example output. Students also showed a strong preference for code-based resources, especially their own, over other more abstracted course materials. In summary, these students provided a rich data set full of insights into their processes and program development when under pressure. As we dug in, these initial findings started to tell a story within our framing question of what problem are they solving? There was a significant difference between instructor expectation and student experience. Where instructors would hope that students would be able to analogically reason between the classical problems covered in class, students had significant familiarity gaps. And what they filled it in with was real-world timings, a focus on the non-concurrency-related parts of the program, and then understandings of the problem that they thought were very important that were just coincidental. Then, where we would hope students would adopt the abstract models used in class, such as design patterns, students went back to the concrete models that they had that familiarity with. They latched onto the single example output. They used code-based resources, especially their own. And as a result, the solution design was affected, whereas we would hope for all valid interleavings to be covered and the correctness conditions to be the primary concern, students reduced the problem space down to something that they could reason about and test accordingly. So they simplified things greatly, which led to very limited simulation settings. This student experience of oversimplification suggests high cognitive load. So what does that mean for PCK? What we're not suggesting is removing all example output from spec sheets, or never using classical problems. If we want to leverage student behavior, well, students find example output very compelling, but it can trigger sequentialist frameworks. In classical problems, they can present analogical reasoning difficulties initially, but could be used to build pattern recognition skills towards more expert behavior like adopting abstract models. Students need more time to build these expert skills in a concurrent programming domain. What we suggest is flipping the traditional script of leading with abstract modeling. Rather, instructors can build student confidence by scaffolding their development of worked examples in many different contexts to gain familiarity. Students can be prompted to reflect on their approaches to develop their own models. Then, abstract models such as design patterns can be introduced, and students may be more willing to adopt them as they recognize them in their models and anchor that knowledge. Productive struggle is incredibly valuable, and we should support students through the process of transitioning out of sequentialist mindsets. As though students may have programming experience, they are still novices in the concurrent programming domain. Thank you for your time.